Artificial General Intelligence, AGI. Artificial General Intelligence, AGI, refers to a type of AI that possesses the ability to understand, learn, and apply knowledge across a wide range of tasks, much like a human does. Unlike current AI systems that are specialized for specific tasks, such as image recognition or language translation, AGI would have the flexibility and adaptability to perform any intellectual task that a human can. This means it could potentially reason, plan, solve problems, and even exhibit creativity and emotional understanding. AGI is still a theoretical concept and has not yet been realized. Achieving AGI would require significant advancements in our understanding of intelligence, learning, and consciousness. The potential impact of AGI is profound, as it could revolutionize industries, solve complex global challenges, and transform society. However, it also raises ethical and philosophical questions about the nature of intelligence, the future of work, and the relationship between humans and machines. Artificial Narrow Intelligence, ANI. Artificial Narrow Intelligence, ANI, also known as weak AI, refers to AI systems that are designed and trained for a specific task. These systems operate within a limited scope and cannot perform tasks outside their designated domain. For example, a chess-playing AI can play chess at a high level but cannot understand or perform tasks related to language translation or driving a car. ANI is the most prevalent form of AI today and includes applications like virtual assistants, e.g., Siri, Alexa, recommendation systems, e.g., Netflix, Amazon, and image recognition software. These systems rely on large amounts of data and sophisticated algorithms to perform their tasks efficiently. While ANI has achieved remarkable success in specific areas, it lacks the generality and versatility of AGI. The development of ANI has greatly enhanced productivity and innovation across various industries, providing tools that augment human capabilities. However, its limitations highlight the need for ongoing research and development to move towards more advanced forms of AI.
Click subscribe to this channel to get more topics you love.
Artificial Superintelligence, ASI. Artificial Superintelligence, ASI, refers to a hypothetical AI that surpasses human intelligence in all aspects, including creativity, problem-solving, and social intelligence. ASI would not only perform tasks more efficiently than humans but also generate ideas and solutions beyond human comprehension. This level of intelligence could potentially lead to rapid advancements in science, technology, and society. The concept of ASI raises both excitement and concern. On one hand, it could solve some of humanity's most pressing problems, such as curing diseases, addressing climate change, and eradicating poverty. On the other hand, it poses significant risks, including ethical dilemmas, loss of control, and potential existential threats if not properly managed. The development of ASI requires careful consideration of safety, ethics, and governance to ensure that its benefits are realized while minimizing potential harms. The journey towards ASI is filled with uncertainties, making it a focal point of discussions in the AI research community. Turing Test. The Turing Test, proposed by British mathematician and computer scientist Alan Turing in 1950, is a measure of a machine's ability to exhibit intelligent behavior indistinguishable from that of a human. In the test, a human evaluator interacts with both a machine and a human without knowing which is which. If the evaluator cannot reliably distinguish the machine from the machine is said to have passed the test. The Turing test has become a fundamental concept in AI, symbolizing the quest for machines that can mimic human intelligence convincingly. While some AI systems have managed to pass limited versions of the test in specific contexts, like chatbots, no AI has fully achieved the general intelligence and adaptability required to consistently pass the Turing test across a wide range of conversations. The Turing test encourages ongoing innovation and serves as a benchmark for evaluating progress in AI. It also prompts philosophical questions about the nature of intelligence, consciousness, and the human mind. Algorithm. An algorithm is a step-by-step procedure or set of rules for solving a specific problem or performing a computation. In the context of AI, algorithms are the mathematical instructions that enable machines to process data, learn from it, and make decisions. They are the backbone of all AI applications, from simple sorting tasks to complex neural networks. Algorithms can be classified into various types, such as supervised learning algorithms, unsupervised learning algorithms, and reinforcement learning algorithms, depending on their learning approach and application. For example, a supervised learning algorithm might be used to classify emails as spam or not spam, while an unsupervised learning algorithm could be used to group customers based on purchasing behavior. The effectiveness of an AI system largely depends on the quality and efficiency of its algorithms. Continuous research and development in algorithm design and optimization are crucial for advancing AI capabilities and solving increasingly complex problems. Big data. Big data refers to extremely large and complex datasets that traditional data processing tools cannot handle efficiently. These datasets come from various sources, such as social media, sensors, online transactions, and more. The characteristics of big data are often described using the three verses: volume, amount of data, velocity, speed of data generation and processing, and variety, diversity of data types and sources. Sometimes, two additional verses are included: veracity, uncertainty of data, and value, potential insights derived from data. Big data plays a critical role in AI because it provides the massive amounts of information needed to train complex models and make accurate predictions. For example, self-driving cars rely on vast datasets of driving scenarios, while recommendation systems use user behavior data to suggest products or content. Managing and analyzing big data requires specialized technologies and tools, such as Hadoop, Spark, and distributed databases. These tools enable the storage, processing, and analysis of big data, allowing organizations to uncover patterns, trends, and insights that drive decision-making and innovation. Data mining. Data mining is the process of discovering patterns, correlations, and insights from large datasets using statistical, mathematical, and computational techniques. It involves various tasks, such as classification, clustering, regression, and association rule learning, to transform raw data into valuable information. In the context of AI, data mining is essential for extracting meaningful patterns that can be used to train machine learning models. For instance, a retail company might use data mining to analyze customer purchase history and identify trends that inform inventory management and marketing strategies. Data mining techniques include decision trees, neural networks, and support vector machines. These methods help in uncovering hidden relationships within the data, enabling businesses and researchers to make informed decisions and predictions. Effective data mining requires a combination of domain knowledge, statistical skills, and computational expertise. Feature extraction. Feature extraction is the process of transforming raw data into a set of meaningful and useful attributes or features that can be used in machine learning models. It aims to reduce the complexity of the data while preserving its essential characteristics, making it easier for algorithms to learn and make accurate predictions. For example, in image recognition, raw pixel data can be converted into features like edges, textures, and shapes. In text analysis, features might include word frequencies, n-grams, or sentiment scores. Effective feature extraction can significantly improve the performance of a machine learning model by focusing on the most relevant information. Automated feature extraction techniques, such as principal component analysis, PCA, and convolutional neural networks, CNNs, are often used to identify and extract features without extensive manual intervention. This process is crucial for handling high-dimensional data and enhancing the efficiency and accuracy of AI systems. Backpropagation. Backpropagation is a fundamental algorithm used in training artificial neural networks. It stands for backward propagation of errors, and is a method for adjusting the weights of the network to minimize the error between the predicted output and the actual output. This process involves two main steps: forward pass and backward pass. During the forward pass, input data is fed through the network to generate an output. The error is then calculated by comparing this output to the true target values. In the backward pass, this error is propagated back through the network, and the weights are adjusted using gradient descent to reduce the error. Backpropagation allows neural networks to learn from data and improve their performance over time. It is a key component of deep learning, enabling the training of complex models with multiple layers. Despite its importance, backpropagation requires careful tuning of hyperparameters and can be computationally intensive, especially for large networks. Hyperparameter tuning involves selecting the optimal set of hyperparameters for a machine learning model. Unlike model parameters, which are learned during training, hyperparameters are set before the training process begins and govern the behavior of the learning algorithm. Examples of hyperparameters include learning rate, number of layers in a neural network, and regularization strength. Effective hyperparameter tuning can significantly enhance a model's performance and generalization ability. Common methods for hyperparameter tuning include grid search, random search, and more advanced techniques like Bayesian optimization and genetic algorithms. These methods systematically explore the hyperparameter space to find the combination that yields the best results. Hyperparameter tuning is crucial because it directly impacts the model's accuracy, speed, and scalability. However, it can be time-consuming and computationally expensive, requiring a balance between exploration and computational resources. Overfitting occurs when a machine learning model learns the training data too well, capturing noise and random fluctuations rather than the underlying patterns. As a result, the model performs exceptionally well on the training data but poorly on new, unseen data. Overfitting is a common problem in complex models with many parameters, such as deep neural networks. To prevent overfitting, various techniques can be employed, such as cross-validation, pruning, regularization, e.g., L1 and L2 regularization, and dropout in neural networks. Simplifying the model or increasing the amount of training data can also help mitigate overfitting. Detecting and addressing overfitting is crucial for developing models that generalize well to real-world data. It ensures that the model captures the true patterns and relationships in the data, leading to more reliable and accurate predictions. Underfitting. Underfitting occurs when a machine learning model is too simple to capture the underlying patterns in the data. It results in poor performance on both the training data and new, unseen data because the model fails to learn the complexities of the data. Underfitting is typically caused by using a model with insufficient capacity or by not training the model for enough epochs. To address underfitting, one can increase the complexity of the model by adding more features, layers, or neurons, or by choosing a more sophisticated algorithm. Additionally, providing more training data or improving the quality of the existing data can help the model learn better. Balancing the complexity of the model is essential to avoid both underfitting and overfitting, ensuring that the model generalizes well to new data and performs effectively in real-world applications. Bias-Variance Tradeoff. The bias-variance tradeoff is a fundamental concept in machine learning that describes the tradeoff between two types of errors that affect model performance: bias and variance. Bias refers to the error introduced by approximating a real-world problem, which may be too complex, with a simplified model. High bias can lead to underfitting, where the model is too simple to capture the data's patterns. Variance refers to the error introduced by the model's sensitivity to small fluctuations in the training data. High variance can lead to overfitting, where the model captures noise rather than the underlying pattern. The goal is to find a balance between bias and variance that minimizes the total error. Achieving this balance typically involves choosing an appropriate model complexity and using techniques such as cross-validation, regularization, and ensemble methods to manage bias and variance effectively. Understanding and managing the bias-variance trade-off is crucial for building robust and accurate machine learning models. Gradient descent. Gradient descent is an optimization algorithm used to minimize the loss function in machine learning models. It works by iteratively adjusting the model parameters in the direction that reduces the error. The algorithm calculates the gradient, or slope, of the loss function with respect to the model parameters and updates the parameters by moving them in the opposite direction of the gradient. There are several variants of gradient descent, including batch gradient descent, stochastic gradient descent, SGD, and mini-batch gradient descent. Batch gradient descent uses the entire dataset to compute the gradient, while SGD uses a single data point, and mini-batch gradient descent uses a subset of the data. Each variant has its advantages and trade-offs in terms of convergence speed and computational efficiency. Gradient descent is fundamental to training many machine learning models, including linear regression and neural networks. It ensures that the model parameters are optimized to fit the data, thereby improving the model's performance and accuracy. Exploratory data analysis, EDA. Exploratory data analysis, EDA, is an approach to analyzing datasets to summarize their main characteristics, often using visual methods. It is a crucial step in the data science process, allowing data scientists to understand the data, uncover patterns, spot anomalies, test hypotheses, and check assumptions using summary statistics and graphical representations. EDA involves techniques such as plotting histograms, scatter plots, box plots, and correlation matrices to visualize the data distribution and relationships between variables. It also includes calculating measures of central tendency, mean, median, mode, and dispersion, variance, standard deviation, range. The insights gained from EDA guide further data preprocessing, feature engineering, and model selection steps. By exploring the data thoroughly, data scientists can make informed decisions, ensuring that the subsequent modeling process is based on a solid understanding of the data's structure and characteristics.